Good morning, everyone. I hope you're all well. Dr. Bennett here, and today we're going to be talking about centroids of volumes and lines. So this is section 7.4 from the textbook, starting on page 335. And is traditional with this course is that we're going to extend what we've learnt about centroids in 2 dimensions to looking at centroids in 3 dimensions. So first of all, we're going to be looking at centroids of a volume, and we saw last time that if we have a arbitrary blob and we split it up into strips of width dx, we can find these strip areas dA by multiplying the width by the height, and then we can find the x-coordinate of the centroid of the total area of the shape by using this weighted average type formula here. And all we're required to do is plug the information that we have into these integrals and solve for x bar, which is the x-coordinate of the centroid of the area. But what we have when we have a volume is that we have a thickness T associated with these strips as well, right? And if we multiply the area with the thickness, we get a volume, right? So that's what I'm doing here. So I've said I take this formula here, I multiply the area, which is the integral of x with respect to A, multiply it with a thickness T to get a volume. So this formula here can be written in terms of integrals over the volume of this shape, like so. And similarly, we find the y-coordinate and now also the z-coordinate, because remember now we're working in 3 dimensions, in the same way, right? So there is a special case regarding this, and that is if we have a volume with a uniform thickness. So the thickness of the volume is the same across the whole shape. Think of something like a coin, for example. And in that case, the centroid is going to be, the coordinates of the centroid is going to be midway between the 2 surfaces of the shape, right? So that should be fairly intuitive to you. And to show you an example of that, what we have down here is an example of this triangle shape, right? So it's basically half of a 3x3 square that's been cut in half. It's got uniform thickness of 0.4, right? And it's centered about the x-axis. And if we wanted to find the coordinates of the centroid, then because we know that this is a standard shape, we can go into the textbook appendices. Here, like Appendix B, we look for properties of the shape that we're trying to consider, and we see here at the top of page 578 where the textbook discusses properties of a triangle. And it says that the centroid of the area of a triangle is 2/3 along the base and 1/3 of the height. So that will give us the x bar and y bar coordinates of the triangle. And then if we remember that if the shape has a constant thickness or a uniform thickness, then the other coordinate of the centroid is going to be midway between the 2 surfaces, right? So that's what I've done here, is I've used the standard results to find the x bar and y bar coordinates. So x bar was going to be 2/3 along the base, which is 3. So 2/3 of 3 is 2. And y bar is going to be 1/3 of the height, so 1/3 of 3 is 1. And then the z bar coordinate is going to be centered between the two surfaces, right, because it's of uniform thickness, and therefore the z-bar coordinate is going to be 0 because this shape is centered along the x-axis. So the final answer, or the coordinates in 3D of the centroid, x bar, y bar, z bar, is going to be 2, 1, 0. So before we get into some examples proper, let's quickly discuss the centroid of a line. It's a similar kind of technique to finding the centroid of a line, a centroid of an area or a volume. Basically what we do is we split up our line into little segments, right, of width dx and of height dy, right, and we call these little segments differential elements of the line, and we can work out the length of this piece. So basically we're approximating this curve, in this case with a straight line joining the two edges of the line segment. We can find out the length of this differential element by just using trigonometry, right? Pythagoras' theorem. We square root the squares of the sides of the triangle. So we square root the square of dx, change in x, plus the change in y, square rooted. And if we factorize dx out of this expression, we can rewrite it like this. And that's going to be a useful form for us when we're applying the integral equations, because now we have something to integrate with respect to when we plug this into our integral equations. So down here, this is how we find the coordinates of the centroid. Similar kind of expressions as before, but now we're integrating over the line, the length of the line. So we have the coordinate, the x coordinate of the centroid given by the integral over the length L of x with respect to L, and then we scale it like the weighted average like we've seen for volumes and areas. So that's how you find the centroid of a line, but there's a couple of things that we need to remember when discussing this type of thing. And that is that the centroid of a volume, an area, of a line, whatever, isn't necessarily on the body or the line or the area, right? So think about these two couple of special cases here. For example, think about a ring. The centroid of that area is going to be not on the area itself, it's going to be in the middle, right? And the same can be said for something like this kind of line. The centroid of that line is going to be off of the line, right? It's going to be somewhere down here. So that's just a couple of things to remember when trying to find these centroids. So now let's go ahead and have a look at a couple of examples. This first example I've got here is regarding the centroid of a volume of this shape here, which is kind of like a cone shape, I guess. And this volume is found, or is made from when we rotate this line, y equals x minus 0.2x squared around the x-axis. So if you imagine this line here, this top line here is given by this expression here, and if we rotate that line around the x-axis 360 degrees, it generates this volume that's in this kind of cone shape. And the question is to determine x bar, which is the x coordinate of the centroid of this shape, right? And we know that the length of the shape is 2 meters, because this point here, which is in the center of this, I know I haven't drawn it particularly well, but this is going to be a circle right at the end here, where it's got a constant radius. The length of the centered around the x-axis, right, and the length of this shape is going to be 2 meters long. So from the theory that we've just discussed, we know that we're going to have to use this formula here, the formula for the x-coordinate of the centroid for a volume, right? But in order to apply this formula, we need to work out what dV actually is. Well, as we said, dV is the small volumes that are generated from splitting up the volume into strips of width dx that have a thickness associated with them, right? So dV is nothing more than the cross-sectional area of this shape multiplied by the width of the strip, so to get a volume. Now the cross-sectional area of this shape is just going to be a circle, right? So we know that this part here is going to be pi r squared, and r, which is the radius of this circle, is going to be defined by the equation of the line defining the edge of the shape, right? So we plug in the equation of the curve into this equation to get pi into x minus 0.2x squared all squared multiplied by dx, and if we expand that and tidy it up a little bit, we end up with this expression here. So therefore we can go ahead and plug our expression for dV now into this integral equation, and I've taken pi, because it's a constant, out of the front of the integral. We're integrating between x equals 0 and x equals 2, right, from up here. And this is my expression for dV. So it's this stuff from here multiplied by dx. Made a little mistake there, this should be dx multiplied by x, right, from here. And then just the integral over v of dV down here. So if I perform that integration on those expressions, tidy it up a little bit, work out what the value of this is between x equals 0 and x equals 2, I should get 1.41 meters as the x-coordinate of the centroid of this shape. So just make sure that you can perform that integration and get the same answer. So now let's have a look at a quick example on how to find the centroid of a line. So here we have y equals x squared between x equals 1, x equals 0 and x equals 1. So y equals 1 at this point, right? And the question is to find the coordinates of the centroid, x bar, y bar. So from what we've just discussed regarding the centroid of a line, we know the length of the differential element dl is given by this expression, right? So in order to plug this expression into our integral equations, we need to work out what dy by dx is. So if y equals x squared, we can work out the derivative of that, which is 2x, and then we can find the square of the derivative. So we just square this to get 4x squared, and then we can go right ahead and plug this into the equation for the differential element dl to get this. So now it's this which goes into our integral equations for x bar and y bar, right? So the problem that I've got here is that everything is going to have these square roots floating around. And just a bit of a word of advice here is that this class, as in statics, is not a test of your integration skills, right? So you probably wouldn't be asked to solve something like this with all of these square roots floating around in an exam or a class test, for example, because it's unreasonable to ask you to do that kind of thing here. It's not a test of integration, it's a test of applying the concepts of finding the centroid of the line. So If you'd like to check or practice your calculus, please go ahead and try to solve these integral equations, but I'll just leave it here with the solution to show what you should expect when performing this integration. When we do the integral equation to find the y coordinate of the centroid, what I've done here is that I've left everything in terms of x squared so that I don't have to re-find this expression up here, right? So you'll notice I need to integrate y with respect to dl with respect to L, right? And y is equal to x squared, so that's why I've just replaced y with x squared, and then dl just stays the same. So then if I do this integration, I should get the following result. So again, that initially looked like a fairly straightforward example because it's something that's quite common and that we're used to seeing, the function y equals x squared, but that actually led to some quite complicated integration down here with all of these square roots floating around. So again, you won't be expected to perform anything like this in a class test or in the final, for example. It's not a test of your integration skills, it's a test of applying the concepts of finding the centroids of the lines. So finally for today then, let's have a look at an extension to this theory to look at centroids of composite volumes. But before we do so, to keep up tradition of discussing my daily beverages, I'm on the Arizona iced tea today, raspberry flavour. Now my feelings about my preferences for the best Arizona iced tea are not as strong as they are for the Gatorade flavours. I like them all pretty much equally. Even the plain sweet tea one is good. Peach is obviously very good as well. So if you have any real preferences for your Arizona iced tea, let me know in the comments below. But I'm pretty sure I've tried all of them by now. Anyway, so let's have a look at this example of a centroid for a composite volume. What we do is we find the centroid of each individual piece, and as we've seen before, we then average that over the whole volume. So this example here that I have, example 3, is basically a cone and a cylinder stuck together. They both have radius capital R. The cone has length A and the cylinder has length B. I'm keeping it quite generic just to show you how the algebra works. But the question here is to find the centroid of the composite volume, so the cone and the cylinder stuck together. So we know we're going to have to use this formula down here as we've just discussed, where we find the individual coordinates of the centroid and then average it over the volume. But because we're dealing here with standard shapes, again, the appendix, properties of areas and lines, is going to be our friend, the one from the textbook, right? So you're going to be allowed to use this in the final, so you don't need to commit any of this stuff to memory. You just need to know what stuff is on here and where to find it. So if we have a look over here, we can see properties of volumes. We have a cylinder down here, so that tells us the formula for the volume. It also tells us where the x coordinate of the centroid is. So we're going to use those standard results. And also if we flick over the page, we can see standard results for a cone that tells us where the x bar coordinate is. It also tells us the volume, and those are the pieces of information that we're going to need to put into our formula. So using those standard results from the textbook, I've just found the volume and the x bar coordinate for both the cone and the cylinder. So that's come straight from the standard results from the appendix in the textbook. The only thing to remember here, as I've written in blue, is that the x bar coordinate, so the coordinate of the centroid of the cylinder is halfway along the cylinder, but you need to remember to add on how it's been shifted along the x-axis, right? So it's positioned starting at a distance of a from the origin, right? So I need to remember to add on a to the x bar coordinate of the cylinder. Hopefully that makes sense to you. So then all you need to do from there is put these two different pieces of the formula into this expression here. So first of all, I've just done x1, which is what I'm calling x1 bar, which is for the cone, multiplied by v1, which is the volume of the cone, plus x2 bar, which is the x bar coordinate of the cylinder, multiplied by the volume of the cylinder, divided by the total volume of the composite shape. So all of this stuff will be on the formula sheet should you need it in an exam. So all we're focusing on here really is the application of these formulas and how to use them. So I hope you're all okay. I hope you're all managing to stay healthy. I hope you're keeping up with the online instruction and you're finding it okay so far. I hope you're all managing to at least get out of the house and get a little bit of exercise, or whether it's a walk or a run or going cycling or something, just to clear your head a little bit. I find it helps me out a lot. I know it's tough, but hopefully you're keeping up with it okay online so far. So here are a few scenes to perhaps inspire you to go out and clear your head a little bit. Cheers.